Hello! In this last video lesson of Unit 1, we are talking about combustion analysis. So this is essentially the only new thing that you'll see on the Unit 1 test that you did not do in Pre-AP. But it is still based on that empirical formula calculation. It's a technique used to find the empirical formula for a hydrocarbon. So a hydrocarbon is a compound that mainly contains only carbon and hydrogen. Sometimes it might also have oxygen or sulfur or nitrogen thrown in there. So first off, before we get into combustion analysis, let's review our standard combustion reaction. In a standard combustion reaction, our hydrocarbon always reacts with oxygen to form CO2 and water. It doesn't matter what that starting hydrocarbon is, CO2 and water will always be the products, and that hydrocarbon always has to have oxygen to react with. So one thing we can kind of think about here is our fire triangle. We need fuel for a fire, which would be our hydrocarbon. We need oxygen to keep that fire going, and we need a spark to ignite it. So here in this unbalanced chemical equation, we see our hydrocarbon and the oxygen. Again, the products are always going to be CO2 and water. So the whole idea behind combustion analysis is that all the carbon from the hydrocarbon ends up in the carbon dioxide product. And all the hydrogen from our hydrocarbon ends up in that water product. So in a combustion analysis problem, they're going to tell you how much CO2 and how much water was produced. So we can use that amount of CO2 formed to figure out how much carbon was in our original hydrocarbon. And we can use the amount of water formed to figure out how much hydrogen was in our original hydrocarbon. Let's take a look at the steps needed to solve a combustion analysis problem. Again, a combustion analysis problem is going to give you the mass of carbon dioxide formed and the mass of water formed. We need to take both of those and convert to moles. Once we figured out how many moles of each are formed, we're going to figure out how many moles of carbon were in that CO2 and how many moles of hydrogen were in that water. That's going to tell us how many moles of carbon and how many moles of hydrogen were in our original hydrocarbon. Like the hydrocarbon that we saw in that last unbalanced chemical equation, sometimes it might contain something which is not carbon or hydrogen. So in that last little reaction we saw, it contained oxygen. So we could find the mass of oxygen by subtracting out the mass of carbon and hydrogen. And we would need to convert that mass of oxygen that we found to moles as well. Once we know the moles of carbon, hydrogen, and any other element that might be in our hydrocarbon, we can just then use our empirical formula calculation, where we're taking our mole values, dividing by small, and multiplying till whole. So let's try this out. So here we perform combustion analysis on a hydrocarbon that we backed that up a slide. We need to be on number 1 to start. So we combusted a 0.8233 gram sample of a hydrocarbon. That hydrocarbon contained carbon, hydrogen, and oxygen. It tells us how many grams of CO2 are produced and how many grams of water are produced. So our first step here is going to be to take the mass of the CO2 and the H2O that we have and figure out how many moles of each of those compounds that we formed. Once we've found our moles of CO2, we can go one step further and figure out how many moles of carbon that were used to form it. So since every 1 mole of CO2 contains 1 mole of carbon, we can find that this is going to have 0.05556 moles of carbon. All that carbon that was in the CO2 we just accounted for. Again, all the carbon from the hydrocarbon ended up in the CO2. So now I know that my hydrocarbon started with 0.05556 moles of carbon. We need to go and do that same thing for hydrogen. We need to figure out how many moles of hydrogen in our water. All the moles of hydrogen that ended up in our water started in our hydrocarbon. So we're going to start by finding the moles of water that were formed. And we know that for every 1 mole of hydrogen, every 1 mole of water, there are 2 moles of hydrogen. So in our water, there was 0.06663 moles of hydrogen. All those moles of hydrogen in the water came from the hydrogen in that hydrocarbon. At this point, we have our mole values for the carbon and for the hydrogen, but remember this hydrocarbon also contained oxygen. So we need to find our mole value for the oxygen. To do so, we're going to have to find the mass by subtraction. We were given the original mass of that sample. So I know how many moles of carbon and moles of hydrogen were in that sample. So if I find how many grams of carbon and grams of hydrogen in that sample there were, subtract them out, that's going to tell us how many grams of oxygen are in that sample. Again, to find the amount of oxygen in our hydrocarbon, we're going to need to take the total mass of that sample, which was 0.8233 grams, and subtract out the mass of carbon and the mass of hydrogen that we just solved for. When we subtract out our grams of carbon and hydrogen from the grams of the sample, that's going to leave us with 0.0888 grams of oxygen. And now we're on the right track to find our empirical formula. To find our empirical formula, we need the mole values of all these elements. So if I've already found my moles of carbon and my moles of hydrogen, we're also going to need our moles of oxygen. Once we've found our moles of oxygen by dividing by the molar mass, we're ready to go into the remaining empirical formula steps, which would be divide by small and times till whole. When we divide by small, which is the 0.00555 moles of oxygen, we get 10 carbons, 12 hydrogens, and 1 oxygen. We already have all whole numbers, so that becomes our empirical formula for this hydrocarbon. That empirical formula is going to be C10H12O. We have 3 more examples on the following page. I recommend that you pause the video, try and work these out on your own, and then when you're ready and you have it done, go ahead and resume the video for the solution. On number 2, our combustion analysis is for a hydrocarbon that only contains carbon and hydrogen. We're producing 1.83 grams of carbon and 0.901 grams of water, 1.83 grams of carbon dioxide. So in this case, all the carbon that's in CO2 still came from our hydrocarbon. And all the hydrogen that's in our water also came from our hydrocarbon. But since this hydrocarbon doesn't have any extra elements, we just don't have that subtraction step. So that's going to simplify this problem compared to number 1. We're still going to be aiming to find our mole numbers for carbon and hydrogen. So to do so, I need to take that 1.83 grams of carbon dioxide and figure out how many moles of carbon are contained within there. So from our 1.83 grams of carbon dioxide, we have 0.0146 moles of carbon. That means we have 0.0416 moles of carbon in our hydrocarbon. We need to go and follow that same step for our hydrogen in water. Figure out how many moles of hydrogen are in that 0.901 grams of water we produced. Once we've completed that, we now have our mole values for each of our elements in our hydrocarbons. Again, we did not have that additional subtraction step. So now we're good to follow the rest of our empirical formula steps. We got to moles. Now we need to divide by small. Dividing by small does not get us to whole numbers quite yet, so we need to times till whole. That's going to give us a ratio of 2 carbons per every 5 hydrogens, making our empirical formula for this hydrocarbon C2H5. Continuing on to number 3, we have a multiple choice question here. So that means that we are trying this out without a calculator. So again, recommended you try this out on your own. Resume the video when you're ready to check for the solution. In number 3, we see the unbalanced reaction for a hydrocarbon, and we are told that at STP we are producing 1.5 liters of CO2 and 1 liter of water. We're looking for that empirical formula. If we're looking for an empirical formula, the first thing we always need to do is get to our mole values. Even though this one doesn't start in grams like the other ones that we've seen, we can still find the moles of carbon in those liters of CO2 and the moles of hydrogen in those liters of water. Since this hydrocarbon only contains carbon and hydrogen, again, we do not see that extra subtraction step. So when we set up our conversion for our liters to CO2 to moles of carbon to find that mole number, we then need to simplify this because it's multiple choice. We're working without a calculator. So what I did was round that 22.4 to 20. That gave me 1.5 over 20, which I thought of as 15 over 20, which is 3/4 or 0.75. But because we have that extra factor of 10 we're dividing by and the 1.5, since it's not 15, we're moving that decimal back one. We have 0.075 moles of carbon. So let's look at finding our moles of hydrogen. So when I found my moles of hydrogen in the 1 liter of CO2, again I rounded that 22.4 to 20, which gave me 2 over 20, which is 1/10 of a mole for hydrogen. Our next step in the empirical formula process is to divide by small. When we divide by small, we get 1 and 1.33. Doing that math, the 0.1 divided by 0.075, I went ahead and moved the decimal back one on both the numerator and denominator, because if I move that decimal by the same amount in the numerator and the denominator, the ratio doesn't change, it's the same value. So I get 1 divided by 0.75. Well, I know 0.75 goes into 1 once. I'm left with the quarter left over, and a quarter is a third, or 0.33, of our 75 that we have there. So that's 1 1/3. We didn't get to whole numbers though, so we still need to times till whole. To get to a whole number, since we have 1 1/3, we're going to want to multiply by 3, giving us 3 carbons and 4 hydrogens, which is going to be answer choice D. So again, on number 4, take a moment and try it out on your own without a calculator. Resume the video when you're ready for the solution. On number 4, we have 0.8 grams of an unknown hydrocarbon. We're making 26 grams of CO2 and 7.8 grams of water. This hydrocarbon only contains carbon and hydrogen, as we can see from our answer choices. So we're still starting with the same steps, finding our moles of carbon and our moles of hydrogen that were produced, because moles of carbon and hydrogen that are produced within the CO2 and water is equal to the moles of our original hydrocarbon. To find my moles of carbon, once I have that dimensional analysis set up, I'm going to go ahead and simplify by dividing by 2. That's going to give me 13 over 22. Well, 13 over 22 is a little over 1/2. 1/2 would be 11 over 22. So I'm going to estimate this to be about 0.6 moles of carbon. We need to go and do the same thing for hydrogen, figure out how many moles of hydrogen are in our 7.8 grams of water. So once I have this set up, I'm going to look at where I can round and simplify my numbers. I'm going to go ahead and round this 7.8 to just 8. 8 times 2 is 16, so this is going to be approximately 16 over 18. Well, 16 over 18 is not quite 1, but I also want to round to numbers that work closely or work well with each other. Well, since it's not quite 1, I have 0.6 moles of carbon. I'm going to go ahead and call this approximately 0.9 moles of hydrogen. So now both of my mole values for carbon and hydrogen have a factor of 3 in them, which is going to make the rest of my math a little bit easier. Now that we have those mole values, we can go and divide by small. When we divide by small, we get 1 for our carbon and 1.5 for our hydrogen. So to find our hydrogen, we did 0.9 divided by 6, which is the same thing as 9 over 6. 6 goes into 9 1.5 times. We didn't get to whole numbers, so we need to multiply it by our lowest factor that will get us to whole numbers. That smallest factor is going to be 2, giving us 2 carbons per every 3 hydrogens, making our empirical formula C2H3. The answer to number 4 is B. So that is some combustion analysis. Hopefully you got to try out a few of these practice problems on your own. If not, I highly recommend that you do before your test rolls around.